Every diagram of our solar system stops at the same place: Pluto, the Kuiper Belt, the orbit of Sedna, then a vague white space and the words interstellar space written in the corner, as if there is nothing else worth showing past that point. This is wrong. Past the orbit of Pluto, past the Kuiper Belt, past even the spherical shell of frozen comets that astronomers call the Oort cloud, there is something extraordinary. A boundary that took our species 50 years to detect. A region of space that our textbooks have only just started describing. And inside it, two human-made objects that are right now transmitting back what they find. The boundary is the Heliopause. Past it lies the very local interstellar medium. And the two objects are Voyager 1 and Voyager 2, currently the only spacecraft humanity has ever sent into the deep cold between the stars. What are they actually finding out there? What does space look like beyond the bubble of our own sun? The answer is stranger than the textbooks ever predicted. Before we can understand what the Voyagers are finding out there, we need to understand exactly what they crossed. The sun does not just emit light and heat, it also emits a continuous wind of charged particles, mostly protons and electrons, traveling outward from the surface at speeds of hundreds of miles per second. This solar wind streams in every direction, filling the entire space within our solar system. Every planet, every asteroid, every comet swims through it constantly. The wind blows outward, and eventually it weakens. Far from the sun, somewhere between 80 and 100 astronomical units, the solar wind slows to subsonic speeds. The deceleration zone is called the termination shock. Past it, the wind is still flowing outward, but more slowly and turbulent. This region is the heliosheath, and it is roughly 30 to 40 AU thick. And then comes the actual boundary, the heliopause. The heliopause is where the solar wind finally stops, blocked by the pressure of the interstellar medium pushing inward. Think of a ship moving through water. The ship pushes a bow wave ahead of it and leaves a wake behind. The heliosphere does exactly that on a scale that dwarfs the planets. The sun is moving through the galaxy at roughly 514,000 miles per hour, and that motion compresses the heliosphere on the leading side and stretches it into a long tail on the trailing side. The teardrop shape is real, the bubble is moving. The leading edge of the heliopause sits about 120 astronomical units from the sun, about 11 billion miles away, 3 times farther than Pluto's orbit. Once a spacecraft crosses that boundary, it has officially left the sun's electromagnetic neighborhood. For the first time in its existence, it is in a region where the sun's solar wind is no longer the dominant force. The interstellar medium takes over. Voyager 1 crossed the heliopause on August 25, 2012. The crossing was not visual. There was no flash, no marker, no shimmering wall. What happened was that the plasma instrument suddenly registered something specific. The density of charged particles around the spacecraft jumped by a factor of 40 in a few hours. Inside the heliopause, the solar wind dominated. Outside, the colder, denser interstellar plasma did. That density jump was the door slamming shut behind Voyager 1. Voyager 2 followed on November 5, 2018, more than 6 years later. Different trajectory, different sector of the heliosphere, slightly different distance, same fundamental measurement. Both spacecraft confirmed the boundary's existence and its rough location, and both are still beyond it today, sending back data. Beyond the heliopause, the rules change. Everything we know about the space immediately around our solar system has to be relearned, one Voyager measurement at a time. The first big finding from interstellar space came as a surprise even to the team that designed the mission. The space outside the heliopause is full of energetic radiation, far more than expected. Inside the heliosphere, the sun's magnetic field deflects most of the high-energy cosmic radiation streaming in from the rest of the galaxy. Cosmic rays are atomic nuclei, mostly protons, accelerated to nearly the speed of light by ancient supernova explosions across the Milky Way. They have been bombarding our region of space for billions of years. Earth's atmosphere and the sun's magnetic shield together absorb most of this radiation before it reaches the surface. We do not feel it, we do not see it. Voyager 1 saw it the moment it crossed the heliopause. The cosmic ray flux outside the heliosphere is about to double what it is inside. The intensity climbs sharply as the spacecraft moves outward and then plateaus. This was the first quantitative confirmation that our local interstellar environment is genuinely hostile in a way the inner solar system is not. Anything biological sent on a multi-decade interstellar mission would be exposed to a steady rain of nuclei moving at relativistic speeds. The protective bubble we live inside is not just a feature of the textbooks. It is, in a real sense, the only reason complex life can exist at this distance from the galactic center. The second finding was the plasma itself. The interstellar plasma around Voyager 1 has a density of roughly 0.1 particles per cubic centimeter. For comparison, the air you are breathing contains about 25 quintillion molecules in the same volume. Interstellar space is about 10 trillion times less dense than Earth's atmosphere. And yet, by the standards of the universe, this density is meaningful. The empty space between galaxies is even thinner. The space inside the local interstellar cloud, where Voyager 1 currently is what astronomers consider warm and dense interstellar gas. The temperature of that plasma is around 7,000 Kelvin, hotter than the surface of the sun. Hot enough that if you could somehow expose human skin to it, your body would not register heat at all, because the gas is too thin to transfer meaningful energy to anything it touches. The temperature is real, the thermal effect is undetectable. This is one of the genuinely strange properties of low-density plasmas. Voyager 1's plasma wave subsystem, called PWS, has been monitoring this medium ever since the crossing. In 2017, the team detected something unexpected in the data: a persistent, faint, narrow band emission. A continuous tone quietly humming through the interstellar plasma, allowing Voyager 1 for the first time to measure plasma density without needing a solar shock event to trigger the readings. The interstellar plasma is, in a real sense, audible, and it is much more textured than the original models predicted, with density fluctuations on scales of less than 0.03 astronomical units. Then, in early 2025, something stranger happened. The PWS instrument detected an abrupt anomaly, a signal that did not match the expected background. Specific cosmic ray fluctuations and magnetic field shifts that did not fit any of the established models of the local interstellar medium. The science team had not yet published a definitive explanation, and they have been careful to avoid speculation. But the data exists. There is something out there ahead of Voyager 1 that the existing theory does not account for. A possible structure in the interstellar magnetic field. A boundary nobody had predicted. The investigation is ongoing. There is also a third element of the interstellar medium that the Voyagers are encountering, even if they cannot directly measure it in detail: dust. Interstellar space contains microscopic grains of carbon, silicate, and ice. They are extraordinarily small, smaller than a single bacterium, and extraordinarily rare. Estimates put the typical density at less than 1 grain per million cubic meters. But these grains drift through space at relative velocities of around 16 miles per second compared to the spacecraft. At those speeds, even a single grain hits with the kinetic energy of a small bullet. Voyager 1 and Voyager 2 are encountering these grains continuously. The dust contributes a measurable component to the plasma wave readings, and over decades it slowly abrades the exterior surface of the spacecraft. Future interstellar missions designed specifically to study the dust population in detail would be able to characterize this material with much higher precision. The grains are thought to come from supernova remnants, evolved stars shedding their outer layers, and the long, slow chemistry of the interstellar medium itself. Each grain is a tiny sample of stellar nucleosynthesis, a frozen record of stellar processes that took place millions or billions of years ago, scattered across thousands of cubic light years and now drifting past our spacecraft. Every model of interstellar space we wrote before 2012 was a guess. Every Voyager measurement since has been a correction. Magnetic fields are not visible, but they are real, and they shape the way charged particles travel through space. Inside the heliosphere, the sun's magnetic field dominates, and it has a specific organized structure called the Parker spiral, named for the physicist Eugene Parker, who predicted it in the 1950s. Outside the heliosphere, the field belongs to the galaxy. It has a different orientation, a different strength, and a different organization. When Voyager 1 crossed the Heliopause, scientists expected the magnetic field around the spacecraft to immediately reorient itself, to shift from solar to interstellar in a clean, fast transition. That did not happen. What Voyager 1 measured was a magnetic field that, in terms of orientation, looked almost exactly like the solar field. Same direction, same general pattern, yet the spacecraft was, by every other measurement, in interstellar space. The plasma was different, the cosmos ray flux was different, but the magnetic field was somehow still pointing the way it had pointed inside the heliosphere. This was a major puzzle. It made some scientists initially question whether Voyager 1 had actually crossed the boundary at all. Maybe it was still in some unknown transition zone. Maybe the heliopause was not where the data said it was. The eventual explanation came from a separate NASA mission called IBEX, the Interstellar Boundary Explorer. IBEX is a small Earth-orbiting satellite that maps the heliopause from a distance by detecting energetic neutral atoms produced when the solar wind collides with the interstellar medium. IBEX showed that the interstellar magnetic field, a few light years out, points in a specific direction, and that direction is roughly 40 degrees offset from what Voyager 1 was measuring. The resolution. The heliopause is not a clean wall. It is a thick, distorted region where the sun's magnetic field and the interstellar field interact, twist around each other, and gradually mix. Voyager 1, in its early years past the boundary, was still inside the distorted zone. Over time, as the spacecraft moved outward, the magnetic field around it should slowly rotate, eventually aligning with the true galactic direction. By 2025, that prediction came true. The field around Voyager 1 had rotated significantly, approaching the IBEX direction. This was a quiet, profound confirmation. The interstellar medium is not a uniform fog. It has structure, currents, and thick boundaries that take spacecraft years or decades to cross fully. The space outside the heliosphere is not empty space. It is a different country with its own weather, its own currents, and its own border zones. We are only just beginning to map them. There is a hard truth at the center of this story. The Voyagers are dying. Their power source is plutonium-238, which decays at a fixed rate, releasing heat that the spacecraft converts to electricity. Each year, the available power drops by about 4 watts. The instruments are being switched off one by one to conserve what is left. In February 2025, NASA shut down the cosmic ray subsystem on Voyager 1. In March 2025, the low-energy charged particles instrument on Voyager 2. And on April 17, 2026, less than 2 weeks before this video was made, NASA shut down the LECP on Voyager 1 itself after 49 years of continuous operation. It's worth pausing on that number. 49 years. The LECP instrument was designed in the early 1970s, built before the first home computer was sold, and has been operating continuously across nearly half a century of human history. Stamatios Kremigis, the principal investigator who built the instrument, reported that its tiny stepper motor had performed over 8.5 million steps without a single failure. The decision to turn it off was forced by physics, not by any malfunction. There was no failure mode. The instrument simply needed power that the spacecraft could no longer supply. Voyager 1 currently has only 2 science instruments still running, the magnetometer and the plasma wave subsystem. Voyager 2 has 3. Both spacecraft are now over 15 billion miles from Earth, and the radio signals from each of them take more than 19 hours to reach us. The mission team operates with an effective communication delay of nearly 2 days for any round-trip command. NASA engineers are now executing what they initially called the Big Bang Plan, a coordinated set of instrument shutdowns and power rearrangements designed to extend the mission for as long as physically possible. The optimistic estimate is that one science instrument may continue to operate on each spacecraft into the early 2030s. The pessimistic estimate is much shorter. The probes are old, the parts are degrading, and unforeseen failures could end the mission at any time. Which means we have a hard window. Whatever the Voyagers are going to teach us about the deep interstellar medium, they have a few years left to teach it. After that, the data stops. The probes keep moving, but they will be silent. And no replacement spacecraft is currently in flight or even fully approved to continue the work. There are concepts on the table. NASA has studied an interstellar probe mission for years, a dedicated spacecraft designed specifically to push past the Heliopause faster than the Voyagers and explore the medium beyond. The estimated timeline is 50 years from launch to reach 1,000 astronomical units. The estimated launch date, if approved, is sometime in the 2030s. None of the current generation of mission planners will be alive when that probe completes its primary objectives. Until then, our entire knowledge of what genuinely lies past the sun's reach comes from two probes that were launched before personal computers were standard appliances. Two probes that are running on equipment older than the engineers maintaining them. Two probes that every day drift a little further from any chance of being repaired. And the questions ahead of them are still open. How thick is the heliopause? What is the actual structure of the interstellar magnetic field beyond the boundary? Are there shock waves where the heliosphere meets the broader local cloud? What density variations in chemistry await the spacecraft as they move into thinner, hotter regions of the local medium? Will the 2025 PWS anomaly resolve into a known phenomena, or will it turn out to be the first hint of something genuinely novel? Some of these questions will get answers in the next few years. Others will outlive the Voyagers entirely. There is no shame in that. The Voyagers have already given us more than what was reasonable to expect from a mission designed in 1972. Anything more is a gift. We are inside the final chapter of a 50-year scientific story. The chapter ends in silence, but the story it tells is the only first-hand account of interstellar space humanity has ever recorded. What lies beyond the heliopause is not a mystery anymore. We have direct measurements, plasma readings, magnetic field orientations, cosmic ray spectra, and continuous data that no instrument before Voyager could have collected. But not a mystery is not the same as fully understood. Every answer the Voyagers send back creates two new questions. The 2025 anomaly is one example. The unexpected magnetic field rotation is another. The persistence of plasma waves at densities we did not predict is a third. The interstellar medium is more textured, more variable, and more strange than the textbooks of a generation ago suggested. And that is the work of frontier science, to go further than anyone has gone. Take the measurements, send them back, and let the next generation figure out what they actually mean. The Voyagers are doing exactly that. They have been doing it for almost half a century. They will keep doing it in some form until the last instrument falls silent and the radio goes quiet for the last time. After that, the probes will continue outward, no longer broadcasting, no longer reachable, but still moving through the same medium they helped us discover. Now you know what the Voyager probes are actually finding past the heliopause, which raises the obvious question. If these two spacecraft are returning the most important data we have about interstellar space, and they will fall silent within the next few years, why is there no replacement spacecraft already on the way? Why hasn't NASA or any other agency planned a Voyager 3? Watch the video here to find out.